What is the null space of a matrix? Here's the definition. The null space of an M by N matrix A, denoted by null A, is a set of all vectors x in Rn such that A times x is equal to 0. So note that this is a homogeneous system, and therefore the null space of a matrix is the solution set of this homogeneous system. So here's an example. Let A be this matrix, and note that A times this vector 0, negative 2, 1 is simply equal to 0, 0, 0, which is the 0 vector, and therefore the vector 0, negative 2, 1 is in the null space of this matrix. On the other hand, if we multiply this matrix times a different vector, we do not get the 0 vector, and therefore 1, negative 2, 1 is not in the null space of the matrix. In summary, it's very easy to check whether a given vector v is in the null space of a matrix. You simply compute A times v and check whether this product equals 0. So try this on your own. Let A be this matrix and check whether these vectors u and w are in the null space of A. So put the video on pause, we'll check answers together. And here's the solutions. If we take A times u, we get 0, 1, 1. So u is definitely not in the null space of A. On the other hand, A times w, do the product, you get 0, 0, 0. So w is in the null space of A. So note that null A is always a subspace of Rn. To prove this, we need to show that 0 is in the null space and the null space is closed under scalar multiplication and vector addition. So first of all, 0 is in null A because A times 0 is equal to 0. Therefore, 0 solves the homogeneous system. 2. If V is in null A and C is any constant, then C times V is in null A because if you compute A times CV, you can pull the C out in front and you get C times AV, which is equal to C times 0, which is equal to 0. And therefore, CV solves a homogeneous system. If V and W are in null A, and so is V plus W, because if you compute A times V plus W, you can distribute the A, and you get AV plus AW. And this is equal to 0 plus 0, which equals 0. Therefore, V plus W satisfies a homogeneous system. Note that if null A is equal to 0, in other words, 0 is the only solution of the homogeneous system, then we say that null A is trivial. We also call it the trivial null space. Here's an example of a trivial null space. In other words, a very small null space, as small as it can be. Let A be this matrix. Let X be any vector in R2. And let's take a look at what AX equals 0 means. Well, AX is just the vector 2x1, 3x2. That's equal to 0, and therefore 2x1 has got to be equal to 0, meaning x1 is equal to 0. And likewise, x2 has to be equal to 0. That means X is in the null space precisely when X is the 0 vector. It's the only vector in the null space, and therefore the null space is trivial. It's a small null space. Let's look at an example of a medium-sized null space. Not the entire space, but not trivial. Here's our matrix and a general vector in R3. AX equals 0 means we'll compute A times X, and we get this vector. And for that to be equal to 0, that means that X1 has to be 0. And X2 and X3 can be anything. No restrictions. Therefore, the null space of A consists of the vectors of the form (0, x2, x3), where x2 and x3 are any real numbers, What does the null space look like geometrically? Well, x1 has to be 0. x2 and x3 can be anything. Therefore, we're looking at the x2, x3 coordinate plane. Thus, the null space is non-trivial, but it's only part of R3. Let's look at another example. Null space can be big, that is all of Rn. So here's an example with a 0 matrix. Well, to satisfy Ax equals 0, x can be any vector in R4. Thus, the null space is all of R4. Question: how do we determine all vectors in the null space? The answer is that we must solve the homogeneous system Ax equals 0. In an earlier lecture, we learned how to do this. And typically, we'll put the solution in parametric vector form, which is equivalent to expressing the set of solutions, that is the subspace, in terms of a basis. So why is the null space important? The answer is that it helps us understand the solutions of the linear system Ax equals b, as well as express these solutions in a simple way. So here's what I mean. Recall that a linear system has either no solutions or at least one solution. In the second case, you can have either a single unique solution or infinitely many solutions. So in case 2, null A helps us distinguish between the subcases 2A and 2B. And also in case 2B, it helps us visualize the entire solution set of Ax equals b. In particular, 2A occurs when the null space is trivial, and 2B occurs when the null space is non-trivial. In case 2B, that is, the null space is not trivial, let P be any solution of Ax equals b. In other words, A times P equals b. P is called a particular solution because it's not the only solution. It's just one. Every other solution is of the form x is equal to p plus n, where n is in the null space. To get an idea of why this is true, let's compute A times x, where x is equal to p plus n. Distribute the A and you get AP plus AN, but A times n is equal to 0, so this is just equal to AP, which is equal to B. Conversely, it's straightforward to show that every solution is of the form P plus n. Let's picture this geometrically in Rn. The null space is a subspace, and we represent that with a plane cutting through the origin. P is a particular solution pointing in some direction with some magnitude. And if we add vector P to every vector in null A, we end up with this plane translated by P sitting out in space above it. This new plane represents all solutions of the equation Ax equals b. Every vector in the new plane is of the form P plus n, and we call that a general solution of the linear system. In other words, this translated plane is the set of all general solutions. What do we do with null A? What role does it play? Here's a partial answer without details. First, the null space allows us to write all solutions of AX equals B in a particularly compact way. In other words, a general solution is equal to a particular solution plus something in the null space. X is equal to P plus N. 2. Many problems in linear algebra can be expressed as a homogeneous equation AX equals 0. Thus, finding null A solves these problems. And 3, I want to mention that null A is often specified by presenting a basis. So here's a brief review of what we covered here. We discussed the definition of null space, what's meant by a trivial null space, a particular solution of a linear system, and a general solution of a linear system.